Hello everyone, this is George Fahim and I'm going to present to you our work titled Single View 3D Mesh Reconstruction and Generation. This work is done under the supervision of Professor Khalid, Amin and Dr. Sameh Zarif and is submitted to the second International Conference on Artificial Intelligence and Computer Vision, AICV 2021. In this short video, I'm going to give a little bit of introduction to the topic and then go through some of the related work and then finally present our proposed methods and some of the qualitative results. Let's start by discussing what is meant by single view 3D reconstruction. Specifically, we're talking about learning-based methods in which an input image is fed into a neural network, and the task of the neural network is to learn the mapping of this 2D image into the 3D domain to extract some useful information and depict this 2D image in the 3D domain. To achieve this, we can use different 3D representations, for example, using voxels, meshes, point clouds, and more recently, we can use implicit surface functions such as the sign distance function to describe the output of the 3D shape. The general architecture used in SVR is the encoder-decoder neural architecture, in which the 2D input image is fed into a convolutional neural network, and the image passes through a series of convolutional and pooling operations to achieve a feature vector that compresses the useful features of the 2D input image. And then this feature vector is fed into a shape decoder, which can be either an up-convolutional neural network to reconstruct a shape in voxel format, or maybe multi-layer perceptrons to reconstruct meshes and point clouds. The body of literature in SVR can be divided into two general categories: methods that work in the Euclidean space and methods that work in the non-Euclidean space. In the Euclidean-based methods, the most common shape representation used for output is the voxel representation. The voxel-based methods can be further divided into discriminative and generative methods. 3DR2N2 is a discriminative recurrent neural network architecture that can take a single view, encodes it, and passes the encoded image into a grid of LSTM cells, then decode it into the output shape. The output shape can be further enhanced when more views are available. The TL embedding network and 3D GAN are generative methods that can encode the input into a traversable, smooth, latent space that can be sampled to generate novel 3D outputs. In the methods that work in the non-Euclidean space, meshes and point clouds are usually used for shape representation. Point cloud methods, such as the point set generation network, uses a number of stacked MLPs to generate the coordinates of points. Output can be enhanced when the network combines the output of another branch that performs a series of convolutional and deconvolutional operations so that finer details can be captured. The two main approaches for mesh reconstruction are either using a graph convolution network on meshes to deform a template mesh, such as in pixel-to-mesh architecture, or using a differentiable renderer as in the neural 3D mesh renderer architecture. Our proposed method focuses on 3D mesh reconstruction, and we used 3D meshes because it's the industry standard in computer graphics, virtual reality, and games. It's a challenging shape representation, but it's really important to achieve 3D reconstruction using meshes since it's the industry standard. Our method is composed of two modules: the mesh reconstruction module, which performs single view mesh reconstruction by deforming a template sphere, and a mesh autoencoding module that performs autoencoding, which compresses the shape into a latent vector. This latent vector can be manipulated afterwards to recover novel variants of the compressed shape. The two modules are trained consecutively. So we train first the mesh reconstruction module, and the output of the training set is used to train the mesh autoencoding module. The mesh reconstruction module is an encoder-decoder network. The input image is fed into an encoder that consists of a series of convolution operations Then the features are aggregated, flattened, and then fed into a fully connected multi-layer perceptrons to produce the feature vector, which is then fed to the decoder to output a deformation vector. This deformation vector is used to deform a spherical template mesh to finally get to the output shape. During training, a multi-term loss function is used. It consists of a chamfer loss, which is an L2 distance function, loss function, between points sampled from the learned output mesh and the ground truth mesh. Normal loss is also incorporated to reduce the discrepancy between the normals of the ground truth mesh and the learned output mesh. We use also two regularization terms, so these are incorporated into the multi-term loss function, a term that minimizes the edge length to prevent flying vertices, and the term that reduces the difference between the graph Laplacians of the mesh before and after deformation. This regularization term restricts extreme deformation to achieve a smoother output. The mesh autoencoding module is composed of an encoder and a decoder that work on the mesh directly. The encoder compresses the input mesh into a latent vector, then decompresses this latent vector back into the 3D shape. We specifically use the spiral convolution operator instead of resorting to conventional graph convolution operator, which is based on feature aggregation and message passing. To perform the spiral convolution, the vertices of the mesh are first serialized into a fixed length vector on which the spiral convolution operates, thus eliminating the need for message passing and performing convolution in a similar fashion to that used in the structured Euclidean domain. To learn shape features in different scales, the mesh is downsampled using a mesh decimation operation that minimizes the quadratic error while keeping record of the barycentric coordinates of the contracted vertices. This matrix of coordinates is then used in the upsampling process where the contracted vertices are inserted back into the mesh after convolution operations. These two ideas have been previously used in facial meshes, autoencoding only, and haven't been utilized before in single-view reconstruction methods for generic shapes. The training is done using two categories of the ShapeNet dataset, the chair and the sofa categories. And here you can see some of the outputs of the mesh reconstruction module using the held out test set of the shape dataset using these two categories, the chair and sofa. Here are the results of the mesh autoencoding module, where the blue shape is the input and the red shapes are different outputs of the same input shape and are produced by sampling the latent vector to get novel variants of the shape. Thus, we achieve through this work both mesh-based reconstruction and generation of novel variants. So our method can be considered both discriminative using the SVR module and generative using the mesh autoencoding module. The results are promising, but show that the mesh-based SVR is still an open problem that is far from being solved. We have many future directions to work on. These can include implementing a different shape decoder, a more enhanced one to enhance the results of the SVR module. Also working on disentangling the compressed representation of the autoencoder can bring beneficial results so that we can have finer control over the variation. For example, in the chair category, we can specifically reconstruct a chair with longer legs, maybe with armrests or no armrests, etc. We thank you for watching and your interest in our work.